Hello and welcome back. Now we're going to look at some problems for practice. Zoom in a bit here. Okay, so in our first example, we have a radio antenna that broadcasts a 1 megahertz radio wave with a 25 kilowatts of power, or with 25 kilowatts of power. Assume that the radiation is emitted uniformly in all directions. So that's going to be key for our spherical expression of intensity. All right, so I've got part A right here. Okay, so here we're just looking at the fact that we know our frequency. We know that it is equal to 1 times 10 to the 6, and that's going to be inverse seconds or hertz. All right, and then we've got our power given here as 25,000 watts, or 25 times 10 to the 3 watts. All right, so in part A, I'm simply going to use this expression for intensity of just power over the surface area of a sphere. In this case, the radius of our sphere is the distance that was given in part A of 30 kilometers, here converted to meters. All right, so we end up with a fairly small intensity because we're quite far away, even though it was a strong source of 25 kilowatts. All right, in other words, that energy is spread out over quite a large sphere at this point. All right, and so then the intensity is 2.21 times 10 to the negative 6 watts per square meter, because that's always going to be our units of intensity. All right, so let's take a look at part B. So in part B, we're asked for the electric field amplitude at this distance. So we're going to use an expression that's going to relate intensity that we solved for in part A to electric field. So let's flip back and look at our formulas. So when we're looking at our formulas for intensity, we see we have a few options. We have one that has the electric field and magnetic field strength, but of course we don't know the magnetic field strength, although we could find it with the speed of light, I suppose. We absolutely could. But this one is ready to go. All right, so we can use that expression. So let's go ahead and copy that over. All right. All right, so that's going to be directly related to the intensity, again, that we solved for in part A. All right, so let's put that in there. There we are. All right, so then what will that look like? So we'll plug in, or well, rather we'll solve for, because we're not quite ready to plug anything in. So let's go ahead and isolate our maximum electric field, because that's its amplitude. The maximum absolutely represents its amplitude, because the electric field is varying, okay? And so then that's going to be equal to the intensity times 2 times the permittivity constant times the speed of light, all inside a square root. Okay, so then let's then solve for that maximum electric field amplitude. Okay, all right, so let's put this into practice. Let's just get our value of the, in this case, permeability constant. Okay, so that's going to be the, should be 4 pi times 10 to the negative 7. Let's make sure we're getting that. Okay. So I'm going to pull up the value over here from your formula sheet. All right. Okay, so permeability. So there's our speed of light. Should be under the magnetism. Okay, so then we'll have square root. Okay, so then put in the 2.21 times 10 to the negative 6 watts per square meter, multiplied by 2, and then multiply by the permittivity, 4 pi times 10 to the negative 7, and that's going to be in Tesla meters per amp. Okay, and then we'll multiply the speed of light, so 2.998 times 10 to the 8 meters per second. Okay, and since this is electric field strength, we know that our electric field is always going to be, so it's energy per charge, so joules per coulomb, or it can also be volts per meter. And so we'll go ahead with the volt per meter, kind of is the best representation of electric field strength. All right, so let's plug in our numbers and get that answer. So 2.21 or actually let me copy over in my calculator, my unrounded value for this one, for part 2. Zoom in, so zoom out so we can see the whole problem. Okay, so times 10 to the 6 times 2 times 4 pi times 10 to the negative 7 for our permeability constant, and then times the speed of light. Good, and the correct orders of magnitude and everything. So then we get, in scientific notation, 4.08 times 10 to the negative 2 volts per meter. All right, so there is our answer. Excellent. All right, let's move on to our conceptual question. Let's follow up here. So the conceptual question shows the electric field for a plane electromagnetic wave traveling in the y direction. So you can see the y direction is shown here. And we want to consider a point where the electric field is in the plus z direction, because the field is moving in that direction. It's traveling in that direction, or actually the wave is traveling in the y direction. But the field is entirely in the zy plane. And all the amplitudes of the field are z values. Okay, so that's in this three-dimensional graph. There's nothing about the electric field that would be in the x direction, nothing at all, because it is a plane electromagnetic wave. Okay, so then consider a point where the electric field is in the positive z direction. The B field is in what direction? Okay, so to help answer that question, we can draw a common expression or common way of showing the electric field. And so we have that it's always perpendicular to the wave. And so when we're looking at that electromagnetic wave, there's a very good way of drawing it in 3 dimensions, where it'll be kind of coming towards us, coming out of the page and going into the page, depending on what the electric field is doing. Okay, so the best way to show that is that when the electric field has a positive z value, the magnetic field has a positive x value. So it would look a little something like this. No, make that a thicker line. Okay. Okay, so all of those expressions for the B field would be kind of coming out of the page in 3 dimensions, or lying in the y-x plane. So then by the time when we get over here, we'd have B field lines that would look like this. All right, so you can see kind of a fun picture to draw. And there we have it. Okay, so and if we were to kind of add some tracing to it, we'd have something perhaps that looked like this. Right, so here is our electric field coming along like that, right? Because it's sinusoidal, and then our magnetic field coming out of the page will be looking like this. Out of the page and into the page, that is. All right, so you can clearly see. And just to make it clear, this is a 90-degree angle right there. Right, these are all at 90 degrees. They're perpendicular to each other. Excellent. Okay, so what we want then to do is finally answer the question. So it said when the E field is in the positive z direction, then what is happening with the B field? Well, then the B field would be in the positive x direction, as we can see, right? And then when the E field is in the negative z direction, then the B field is in the negative x direction, right? That would be like over here, for example. All right, so hopefully that nature of the perpendicular components of the EM wave is clear. The biggest takeaway is that the wave moves in one direction, the magnetic field moves perpendicular to that direction, and the electric field moves perpendicular to both of them. Okay. All right, let's take a look at example 2. Determine the amount of energy carried in 2 meters of a 4.6 milliwatt helium neon laser beam if the cross-sectional area of the beam is 4.1 times 10 to the negative 6 square meters. Okay, so how much total energy is there in that beam? Okay, so let's think about this. So in this case, we want to take the power and the cross-sectional area, and then relate it to how far, how much time it takes to cover 2 meters, because that will be our delta T. Okay, so first of all, let's think about this. So we know that our energy is going to be our value of intensity times area times delta T. Delta T is the least obvious part, but again, that's just going to be the time it takes the light to cover 2 meters. So we'll say that delta T is going to be our distance over velocity. So it'll be d over v, because that, of course, will give us how much time it took to travel the 2 meters. Not much time, obviously. So then we have our 2 meters, and then divided by our 2.998 times 10 to the 8 meters per second. Okay, so let's get that small number. 998 times 10 to the 8. Okay, so that gives us 6.67 times 10 to the negative 9 seconds. Right? Doesn't take light much time at all to travel such a short distance. No surprise there. Okay, and then we want to then take everything and put it together to find the energy. So then the energy is going to be our, there's one thing that I wrote. We have, I want to think about the power. Okay, because we have the cross-sectional area. We weren't given the intensity. Let me flip back and take a look at that. So let's see, because we have the power spreading out. Were we given the source energy? Yeah, so 4.6. Yeah, so we were given the source energy. That'll allow us to find. Yep. So determine the amount of energy carried. Yeah. So let's go ahead and replace this with our power over 4 pi d, because it's still the distance squared, and then times the cross-sectional area times delta t. Okay, and so then let's plug everything in. So then we'll plug in our 4.6 times 10 to the negative 3 watts. Okay, and then we'll have the distance it covered. Okay, so our 4 pi and then 2 meters squared, because that would be the intensity at that distance, and then we'll multiply by the cross-sectional area, the 4.1 times 10 to the negative 6 square meters, and then multiply by the delta T, because that's the the total energy over that time. Okay, so the amount of energy carried, and yep. Okay, so then we'll multiply by our 6.67 times 10 to the negative 9 seconds. Okay, because then we're getting the entirety of the beam. Okay, so let's plug in all our numbers here. So 4.6 times 10 to the negative 3 divided by 4 pi times 2 squared, and then times our cross-sectional area. Okay, and then multiplied by our time. Okay, so then we should get 2.50 times 10 to the negative 18 joules. Okay, so yep, because we have the weak laser carrying out. It's a very, very, very small amount. Yep, it's a very, very small amount of energy. So basically if we're thinking electron volts, right, with our so it's a fraction of an electron volt, so right basically on that scale. Kind of makes sense. The only thing I'm checking here is making sure that the idea of multiplying by the time it takes to cover the 2 meters, because certainly the 2 meters shows up when we're thinking about determine the amount of energy carried. Let's make sure that makes sense, because I don't want to underestimate the amount of energy, because it's here I'm saying, okay, well, that's the total energy in the beam, but the beam length shows up here with d, so that's where we have the 2 meter distance. So that's giving us the intensity at the end of the beam. So determine the amount of energy carried in 2 meters of a 4.6 milliwatt beam cross-sectional area. So yeah, so okay. So yeah, it kind of makes sense because then we're getting, because certainly then we are getting the total energy that passes. It's sort of like we're letting, that's, so the way I'm interpreting this is that we're getting that 2 meter beam, of light, right? And it's passing over a certain point. So it's like you're letting 2 meters of beam pass over something, or 2 meters of beam be absorbed by something. As long as that is the way that I'm correctly interpreting this problem. So we're at a distance of 2 meters from the 4.6 milliwatt source, and then and the beam has that width, and then at that fixed 2 meters, we're allowing that entire beam then, if let's say it's shut off, we're allowing that entire beam then to end up getting completely absorbed by something at that 2 meters. Okay. Yeah. So that being the interpretation, then that would be the correct value for our amount of energy. Okay. Okay, so let's see, so which ones, so yeah, I'm leaving example 3 for practice. I'll be posting the solution, but I'll leave it up for a while for practice before I make an updated version of the post notes. So you can take a look at that. This one, it's sort of the idea about how energy being absorbed. It doesn't have the ambiguity of the problem above, example 2, so it should be straightforward. You don't have to think about the time. Okay. So it is an interesting problem, however. Now I want to show you one more, though. So the last one that I wanted to show you was example 5, which is mislabeled as 4. So let's fix that. Okay. So we don't have 2 example 4s. We actually have an example 5. There we are. Okay. So again, likewise, example 4, while I'm on that, is going to be left for practice. All right, that one's quite straightforward. But let's take example 5 as the last one I wanted to show you. So in example 5, a 100 kilogram spacecraft has a sail of 3 times 10 to the 4 square meters. So essentially 30,000 square meters. So it's a big sail. That actually is true of a lot of plans for solar sails. They'd have to be very, very large. And it is absorbing sunlight of intensity of 800 watts per square meter. Okay, that's kind of a realistic value for intensity coming from the sun. Depending on your distance from the sun, of course. Okay, so what is the resulting acceleration of the spacecraft? Okay, so what we need to find here is we need to find the change in momentum and then relate that change in momentum to force and acceleration. Okay, so let's go ahead and do that. So then we have that in part A, we have the momentum of absorption is equal to the energy of the light divided by the speed of light. So I'm just going to be using this one here. So it's just going to be U over C. Okay, so that's going to be our expression. So I just have U over C. All right, and so then we want to find the energy of the light. Okay, so we have basically the expression for the watts there. Okay, so then I can go ahead and put that in. So I'm going to have let's write energy, right? So the energy is going to be intensity, and the value here is not in watts. It's actually in the units of intensity, so watts per square meter. So I'm going to have intensity times cross-sectional area. That's just the one that's given, and then times delta T. Okay, so how do we deal with that, right? How are we going to deal with the delta T? Well, you'll see. Okay, it's going to go back to Newton's second law, and then we'll divide by the speed of light. So we're not quite ready to solve that yet because we have to reorganize our expression here. So this right here is the momentum of absorption. Now it's really a change in momentum because the light is, as it's hitting the solar sail and being absorbed by the solar sail, that it's basically warming it up effectively, right? But here really we're not concerned about the heat energy, but instead the mechanical energy and the kinetic energy. But that momentum being imparted on the sail is a change because naturally the momentum was 0, right? So then we have the change in momentum divided by the change in time because I'm going to take this expression and divide both sides of the equation by it. So I'm going to get delta P. I'll leave the absorption there. Okay, let me write it out. And then I'm going to divide by delta t. Now the reason I'm doing this is because delta P over delta T is exactly force by definition. That is the Newton's second law in translational momentum form. Okay, so that is F. That's force. That's the force that the light is putting on the sail. Okay, and then that is going to be equal to the mass of the sail times acceleration. Okay, so now you can see how we're going to solve for acceleration. So then what we're going to get is that the acceleration is then going to be the intensity of the light times the cross-sectional area of the sail divided by the speed of light and the mass of the sail. Okay, so then we'll plug in our values. I'll go ahead, I have space down to do it here because we'll do something really similar in part B. So our intensity, we'll plug in our 800 watts per square meter. We'll have our cross-sectional area of 30,000 square meters. All right, and then we'll be dividing that whole thing by the speed of light. So 2.998 times 10 to the 8 meters per second, and then our mass, 100 kilograms. All right, so that is none other than acceleration. Let's see, is it going to be a giant number? I don't think, but it should be interesting that we can even get anything to accelerate in something, relatively massive like this. Of course, it has to be a very thin sail, right, to be that only 100 kilograms and that large. But the idea is to make these sails out of, sort of like, like nano sheets, right, like carbon sheets that are incredibly thin, so we can have them be very, very large but very light. Okay, and obviously a lot of this stuff, it's not like people are going out and building too many solar cells yet, but this technology has been tested. It has been used on some smaller scales. Okay, so we end up with 8 times 10 to the negative 4 meters per second squared. So 8.00 times 10 to 1. Get my sig figs right. Times 10 to the negative 4 meters per second squared. All right. So this would work for like a solar sail that was, say, black, right? So it's absorbing all of that light energy. That could be especially helpful because of absorbing the energy. It could be doing something with it. It could be powering a transmitter, for example, because it could be turning some of that absorbed energy into a current that could power electronics on board our spacecraft. But if instead we made a sail that was entirely reflective, then we could get significantly more acceleration, because in that case, P reflection, so the change in momentum for a reflective scale is 2u over c, which means that when we solve for everything, we get an acceleration that would be 2I times a over c m. And so it will just be twice the acceleration. So in this case, it would be 1.60 and then times 10 to the negative 3 meters per second squared. Again, not giant accelerations, but you got to think about it. That acceleration has nothing opposing it. There's no friction in space. So that means that the spacecraft would be really slow at first, but let's say it accelerates for 24 hours straight without any opposing force. Well, at the end of that period, it could be going quite quick. Right? So a solar sail is a slow process, but one that gradually does allow spacecraft to pick up significant speeds. The only downside is that, as it moves, it then, of course, moves further and further away from the sun, and the intensity falls off. And it's going to fall off as a square of distance, but it's still accelerating. It's just that the acceleration wouldn't stay at the same rate. All right, so we've seen some properties of light. Let me just finish this video by saying that the big picture here is that we're going to be working with light. We've introduced a few things: the speed of it, the idea of the electromagnetic spectrum briefly, and that this idea that Maxwell's equations are overarching and so on. What I will say is that we're really going to be doing a lot with the optics of light. That's going to be light in a geometric sense. Then we're going to be doing a lot with the wave nature of light, how light can, two light waves can interfere with each other, and how a single light wave can interfere with itself. And then really that's going to be our end of this unit, and we'll move into modern physics. But once we get into modern physics, we'll have an opportunity, after discussing relativity, special relativity, Einstein's theory of special relativity, we actually will have one last opportunity to come revisit light. Because it turns out that there's a more modern version of light. So I bring that up because it's going to be with us till nearly the end of the semester. It's really kind of one of the big cornerstones of this second half of the semester. Okay, I'll see you in the next video.